All right, let's dive into one of the greatest detective stories in the history of science. We're going on a journey that starts with a theory that sounds like a dessert and ends with a discovery that completely flipped our understanding of, well, everything. We're talking about the true structure of the atom.
So imagine it's the early 1900s. This right here is one of the biggest questions on every physicist's mind. They knew atoms were real, sure, but how were they put together? What was the blueprint? The answer was about to come from a truly mind-bending experiment.
But before we get to the big reveal, we have to look at what everybody thought was true. And the leading theory at the time had a pretty tasty name.
Okay, so here's the thinking. A scientist named J.J. Thomson had discovered the electron, this tiny particle with a negative charge. But atoms themselves are neutral, so he figured there has to be some positive stuff in there to cancel out the negative electrons. He pictured it as this big, fluffy ball of positive charge, the pudding, with the little negative electrons scattered inside, like raisins. You know, it actually made a lot of sense at the time.
And pretty much everyone in the scientific community was on board with this. It was simple, it was elegant, it seemed to explain things. But, as you know, science is all about testing your ideas. And this idea was about to face the biggest test of its life. So, enter the hero of our story, a physicist from New Zealand named Ernest Rutherford. Around 1907, he and his team, Hans Geiger and Ernest Marsden, came up with a brilliant way to actually peek inside the atom and put that plum pudding model to the test.
Now, to see what's inside something so small, you can't just use a microscope. You have to shoot something at it. Rutherford's bullets of choice were something called alpha particles. Now, here's the most important part of this whole story, so remember this. Alpha particles have a positive charge. That little fact is the key to everything.
So here's how it worked. You've got a source that's basically spitting out these alpha particles. They get funneled through a screen to make a nice tight beam. Then they shoot that beam at a piece of gold foil that is ridiculously thin. I mean, just a few thousand atoms thick. And then wrapped around the whole thing is a detector screen that would light up with a tiny flash every time a particle hit it. This way, they could track exactly where the particles went.
So the team gets to work, firing away. Honestly, they were probably expecting a pretty boring result, just a bunch of flashes on the screen proving the plum pudding model was right. But what they saw instead, well, it wasn't just unexpected. It was completely impossible.
And this is the heart of the mystery right here. On the left, that's what was supposed to happen. The alpha particles should have just sailed right through the pudding with maybe a tiny nudge here or there. And for the most part, they did. But, and this is a huge but, as you can see on the right, every once in a while, maybe 1 in 8,000 times, a particle would get deflected at a crazy angle, and some even bounce straight back toward where they came from.
This was the question that broke physics. How could this happen? Rutherford himself later said it was as incredible as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. It just made zero sense with the current model.
The plum pudding model was toast. It was dead. There was no way that a soft, spread-out pudding of positive charge could ever have enough force to turn a speeding alpha particle around. They needed a new theory, and they needed it now. And this is where our detective, Rutherford, had his moment of pure genius. He realized there was only one possible explanation. For a positive alpha particle to be repelled so powerfully that it bounced backwards, it must have hit something that was also incredibly positive and unbelievably dense. So he proposed this radical new picture of the atom. He said, forget the pudding. Instead, all of the positive charge and almost all of the atom's mass is packed into an impossibly small, dense point right in the very center. He called it the atomic nucleus.
And those positive particles that made up this brand new nucleus? Well, they eventually got a name, protons. And just like that, the entire model of the atom had been reinvented.
The amazing thing about this new model is that it didn't just explain the one weird result, it perfectly explained all the results. And in doing so, it painted a brand new and frankly very strange picture of the atom.
So let's connect the dots. Why did most of the particles fly straight through? Because the atom is mostly empty space. Why were a few of them deflected? Because they passed close enough to that powerful positive nucleus to get pushed aside. And what about that tiny fraction that bounced straight back? They were the unlucky ones that scored a direct, head-on collision with that nucleus. All of a sudden, all the data made perfect sense.
And just think for a second about how dense we're talking. More than 99.9% of an atom's entire mass is crammed into that tiny little nucleus. The rest of the atom, where the electrons fly around, is just vast, empty space. It's truly wild.
And all of this leaves us with one last fantastic question to think about. If you and me and that wall over there are all made up of atoms that are 99.9% empty space, then why can't you just walk right through it? The answer has to do with the forces between all those electrons, but that's a whole other detective story for another time.